In this video, I'll be talking about PN junction. Now, what is a PN junction? What is it? What's a PN junction? So we have P and we have N, and we have a junction, and we have uh, p-type semiconductor and we have an n-type semiconductor. And what should I say about is, I mean, a single piece of semiconductor material with one portion uh, doped with pentavalent impurity and the other portion doped with the trivalent impurity behaves as p-n junction. In fact, the boundary that's dividing the two halves uh, of such a semiconductor is called a junction. So this is a junction, right? Uh, and uh, and the point is now, when we have a situation like this, we have p-type, we know we have majority of holes. N-type, we have a majority of electrons. Uh, and when it comes to the preparation point of view, when we have to trivially explain the preparation of junctions like this, uh, we can think of, suppose uh, we have we have an n-type material like this, and so this is n-type. Now this is acting as a base. We call it wafer, and and what we do with this is that a small quantity of trivalent impurity, say indium, as we talked about indium in the previous video, it's a trivalent impurity, is present on the thin wafer. Uh, yeah, thin wafer of n-type germanium. So here we have n-type germanium or silicon, whatever we choose, and this indium is then fused into the surface of this n-type semiconductor. So what is done is we infuse this p-type material on the surface of this n-type material, right? So what's happening here? I mean, the p-type semiconductor along with n-type semiconductor wafer forms a p-n junction, right? So this can be a trivial way to explain. Similarly, a p-n junction can be made by fusing a small quantity of pentavalent impurity into a p-type semiconductor, and this will mark the formation of the p-n junction. So there are many approaches of preparing the p-n junctions in the laboratories. Now the point is that is it something like that the way I have shown here? Is it like sandwicking kind of situation? The answer is no. We are not sandwicking a p type material with n type material. What we do is we have a wafer of n type, and we fuse the pentavalent material, pentavalent pentavalent p-type semiconductor by making use of suitable doping like indium, forming a p-n junction. Now, two independent p-type and n-type semiconductor slabs joined end to end, it cannot form a p-n junction. The way I have showed it here, it's not like that you are joining a p-type semiconductor with n-type semiconductor. This is because even the most smoothly polished surface, when pressed against each other, have small area of contact, right? So the surfaces are very irregular. The surfaces between these two p material and n material, they are not smooth at all. There is a lot of there are lots of valleys between these two. So what you do if you do this kind of thing, if you press P against N, you're going to dilute, you're going to contaminate the junction between the two semiconductors. So when we press if we press this P against N, there is a very small area of contact between two. Moreover, even the most clean surfaces may have some contaminations, like minute dust particles, which do not allow the two surfaces to come in atomic contact. Thus, when p-type and n-type surfaces are pressed against each other, there will be discontinuity. There will be complete discontinuity between them, and for the exchange of charge carriers in P region and N region. So P-N junction cannot be formed just by joining a P-type material with N-type material. We need special techniques by virtue of which the P-type material is infused on N-type material. So that's a different piece of study. Now, when we have a p-n junction, we would like to represent this p-n junction in a very block way like this. So we have what we have is we have a p-n junction, right? So if I go with this, so what's happening? We have a p-n junction. Okay, so there is a junction. This is P and this is N, and we understand this P has majority of holes, and it has minority of electrons, and this N has majority of electrons but minority of holes. So at the time of formation of the p-n junction, certainly there is the movement of charge, right? And what happens is that the concentration of holes in the p side, the concentration of holes in the p side is more than that on the n side of the p-n junction, and the concentration of electrons is more than that of concentration of electrons in the p side. So this thing should be clear, okay? And the holes, what holes are going to do here? The holes diffuse through the junction from higher concentration region to the lower concentration region, and uh, uh, and that's holes diffuse through the junction from P region to N region, and combined with electrons in the N region. So here we have holes, and they combine with electrons, electrons in the N region. Okay, and hence get neutralized. Similarly, electrons diffuse from N side, they diffuse they diffuse through the junction from N side to the P side, and they neutralize holes from this side of the p-n junction. So what's going on now? So we have holes diffusing from the p side, and we have electrons diffusing from from n side. So there is a kind of process, the process of combining electrons and holes, and this is what is called as electron hole combination. So we call this as electron hole combination. So it's the concentration that makes the diffusion of holes from p side into n side, and then electrons from n side to p side. When holes diffuse through the junction, the p region near the junction is left with negative ions, or we may call them as acceptor ions. Okay, that's that's the point. Fixed in their positions in the crystal, because originally we have a crystal, and we are doing the whole job on the crystal, where we have a p-type and n-type materials. On the other hand, when electrons diffuse through the junction, the n region near the junction. So in first case we had a region here, and the n region near the junction is left with positive ions. So we have positive ions here, and here we have negative ions. Right, so the n region near the junction is it is left with positive ions, or we may also call them as donor ions, fixed in their position in the crystalline. Now, hence the negative ions or acceptor ions near the junction in p side, and positive ions or the donor ions near the junction of n side form negative charged and positive charged layers or regions respectively. Now this space charge region that we have here on both sides of the p-n junction is taken together, and this whole thing is called as depletion layer. So this whole thing is called as depletion layer, or or the region, because it has no mobile charges. The thickness of this depletion layer is typically of the order of 0.5 micrometers. Now, when we proceed on, I mean, this depletion layer contains positive and negative immobile ions on either side of the p-n junction, right? So the positive and the negative ions, they set up a potential difference. So what is happening is there is a potential difference. There is a potential difference that develops between p-type and n-type semiconductor, right? So what happens? There is the potential difference across the p-n junction, which opposes the further diffusion of electrons and holes through the junction. Now, this potential difference that we have here, this potential difference is called potential barrier. Now, this is called potential barrier because there is no further movement of electrons and holes through this barrier. That's why this is called as potential barrier. The potential barrier is about, as I said, it is of the order of its length is of the order of micrometers, and this potential barrier is of the order of 0.7 volts for silicon, and it is nearly 0.3 volts for germanium, right? Now the point is that if we have the potential barrier here, now this potential barrier can be written in terms of the electric field. So electric field is, so there is an electric field set up divided by D. where this d is the thickness of this depletion layer. This electric field is set up across the junction due to the potential barrier. This electric field is directed from positive charge to negative charge across the junction. So its direction is like this, right? So it is from positive charge to the negative charge in the junction. That can be understood. That can be realized. Now, the electric field that is set up here, this electric field exerts force on electrons in the p region to move towards the n side, and exerts force on holes in n region to move towards the p side. Thus, a drift current begins to flow due to drifting of holes and electrons across the junction. The flow of drift current is opposite. It is opposite. Uh, uh, we have what I call as uh, the drift current that I'm talking about here. The drift current of holes, right? So holes coming from here and the electrons coming from here. Now, the flow of the drift current is opposite. I am trying to tell to the flow of diffusion current, to the diffusion of electrons and holes through the junction. This drifting continues till drift current becomes equal to the diffusion current, because there is potential barrier. The potential barrier is there. That means there is electric field, and there is diffusion. There is drift current, right? And in the process of manufacturing of the PN junction, what happens? This drift current equals to the diffusion current. So when this drift current is equal to the diffusion current, net current passing through this PN junction becomes zero. Now, therefore, the barrier potential of the PN junction that we talked here, it comes by virtue of diffusion, right? But at the same time, once there is diffusion, there an electric field is set up in the depletion layer, and that electric field deflects the electrons and holes and gives birth to the drift current. And in a very short span of time, this drift current equals to the diffusion current. So when this situation reaches, we say that there is no further flow of current in a PN junction. So this is we can demonstrate this thing if I take a situation like this. We have a PN junction, right? And we have the depletion layer. Here we have uh, positively charged ions. Here we have electrons, and here I have P. Here I have N. So I can think of a slope at the point of depletion layer, like this. So this should be the width of the depletion layer, and uh, and uh, and here the energy level is high. Here the energy level is low. So there is a slope. So there is diffusion, and this diffusion is balanced by the drift current. And finally, there is no flow of current across the PN junction. So we have a PN junction, and this PN junction is complete, and can be characterized, and can be used to be analyzed further in the further course of lectures.